All right. So it's a good pleasure to have Pierre Sikivie tell us about how to tell apart WIMPs from axions. So please, Pierre, the stage is yours.
So, Luca, thank you very much for having me. And thank you for coming to this talk. So my title is How Observation May Tell Axions and WIMPs Apart. It's a topic I've been interested in for a number of years. And I've listed here some of the collaborators, including Elisa, and actually some more, but the work I'm going to talk about stops with Elisa. Feel free to ask questions, okay, at any time. So I need not tell you that the evidence for dark matter is very solid. There's evidence from the dynamics of galaxy clusters, from galactic rotation curves, from the anisotropies and the CMBR, and from the bullet cluster. And each one of them has a beautiful picture that you have already seen. There's one picture, though, I couldn't help. Oops. I wanted to show it, which is the Planck sky map, because it's an amazing achievement, of course, to have seen these small fluctuations in the cosmic microwave background, but also to explain them, the power spectrum, in terms of very simple ingredients and a very small number of parameters. And as you know, the ingredients are dark energy, dark matter, and baryons. So this is actually what we know about dark matter for sure, and everyone has agreed upon. So let me ask, what is it actually, or does this constrain the dark matter? And I think the statement there is that the evidence is consistent with cold collisionless dark matter. And as far as the CMBR is concerned, and this is why I showed the picture, when you look at the calculations, what you do is you assign to the dark matter a density. Oops, they're supposed to, I like the long stick actually. You assign to it a density and a velocity field. And it satisfies the continuity equation and the Euler equation. And the Euler equation on the right-hand side is just the gravitational field driving the axion. Axion, I'm prejudiced. But you all have the dark matter fluid, called dark matter fluid. There's no other terms, although some people do add other terms. And of course, the dark matter may have other interactions, but that doesn't actually play a part in the structure formation. Now, this seems very simple, but I think it's in many ways confusing, and it's true. Sometimes the truth may be confusing, because I say it's a collisionless fluid, but a fluid with collisionless, you should not analyze it in physical space, you should analyze it in phase space. The fluids that we are used to, like water and air, are collision full, and you correctly describe them in physical space in terms of a density and a velocity. And the reason this is, like in the case of air, is that a molecule of air only travels a very short distance before it meets other molecules of air. And therefore, this small volume of air has to flow together. It cannot flow through the other air. So everything has to flow together. So there's a velocity field everywhere. A collisionless fluid, and aside from dark matter, we have experience of collisions with neutrinos and light. And light especially is in this room. It is collisionless because light can flow through itself. A collisionless fluid should not be described in physical space, but it should be described in phase space. For example, neutrinos, if you look at the neutrinos here in this room, they can have any velocity distribution and any location in space, physical space, they can have any velocity distribution. So that means they have an arbitrary phase space distribution. And to predict the future of a fluid of neutrinos, you must start with its phase space distribution. So isn't this very confusing? Because I said in the previous slide that a successful description was, of collisionless dark matter is in terms of the density and the velocity. Well, please do ask questions, okay? Because actually I think that this point is often overlooked, and maybe it's trivial to you. I don't think it's trivial. Because I'm saying here, you just need the density and the velocity. Well, actually, that is because it is cold. So you realize that in the case of cold dark matter, the reason you can describe it by a density and a velocity is completely different from the case of air. The case of air is because the fluid is collision full. Here it is collisionless, but it is cold. Actually, so let's give it a more general description by going to phase space. So now this is, I think, why I and everyone else is reluctant to go to phase space, because it is 6-dimensional. It is very difficult to visualize. Since we are little kids, we used to thinking about physical space. Going to 4-dimension is a big struggle. Going to 6-dimension is an even much bigger struggle. But if we talk about the homogeneous universe, then actually all directions are equivalent. Let's take one direction, z, and then its canonical conjugate, which is the momentum in the z direction, which for a non-relativistic fluid is the velocity. The particles lie on this red line because the velocities are proportional to the distances. So this is in principle a complete description of the fluid in the limit where you say it's perfectly cold and you can neglect the velocity dispersion, which is the thickness of the line I drew. Indeed, for the acceptable cold dark matter candidates, WIMPs, axions, and heavy neutrinos, the velocity dispersions are small enough. They're actually smallest for axions, and for reasons I explained, I'm putting an upper limit here. 10 to the minus 8 is sufficiently small. And for this, if you have a neutrino, you have to have a sterile neutrino sufficiently heavy if it's produced by weak interactions in the early universe. You're so quiet, you make me nervous. No questions? Is it okay so far? Yes, please. Yes, Luca.
Okay, we think of it as basically a variance slope with time, right?
Yes, thank you. There's a lot to be said about this picture that probably goes by too fast. The slope of this line is the Hubble rate. And as time goes on, the Hubble rate goes down. So this line becomes thinner and thinner. What happens is that a particle here has positive velocity and just keeps on going. And so this line becomes more shallow. And as I think this is what you're saying, and thinner by Liouville's theorem. Because the density in the line has to be constant. So actually the line really stretches, the volume of it stretches, and the velocity dispersion goes down. And I placed here the velocity dispersion today, and this would be in a homogeneous universe, and I don't worry about density perturbations at this point. Okay? All right. So, but of course, there are density perturbations. So what does that mean for the description? Is that the velocities at some location actually deviate from Hubble flow, and you have so-called peculiar velocities, which appears like wiggles on this line. But up to this point, at every location, you have a definite density, which is the projection of the phase space density onto physical space. Now, this is in the linear regime of density perturbations. If you go further, this line will begin to wrap itself up, like here, where you're forming a galaxy. And now you see that the original description breaks down, because whereas here you have one flow, one velocity at this location, here you have three flows, three cold flows. And where the number can only change from 1 to 3 to 5 to 7 and so forth, always has to be odd number. But where the number changes, say from 1 to 3, you have a caustic, because when you project this down to physical space, the projection of this, so I call this the phase space sheet. It's a 3-dimensional sheet and 6-dimensional phase space. When you project it down onto physical space, you'll have a caustic and accumulation, because the sheet, the phase space sheet, is parallel to velocity space. And when you project it, you have infinite density, formally infinite. It's like I take this sheet and I project it onto the floor, whereas the most projected sheet is where there is a fold, right? You understand this? Okay, great. Let's leave these ideas for a moment and go on. Okay. This is stuff you all know, but it's like church. You know, we repeat stuff that are solid and that we believe in. Today we ask, what is the dark matter? And I think when you do that, it's good to look at history. Earlier, 4 centuries ago, we asked, what is light? Because people 4 centuries ago understood the motion of particles, like planetary motion, but certainly light must have been a mystery. I can turn on the light on and off. Actually, Newton couldn't do this, right? But people were very interested. What's the nature of light? And they thought about that. And they made 2 assumptions. Newton interpreted in terms of a stream of particles, and Huygens in terms of a wave. And I think that's very interesting, because today, some of us interpret dark matter as particles and some as a wave. So we want to know which one is correct. Well, Young and others showed that you can make interference patterns in light, and that shows that it is a wave. But it turns out that's not the final story. Oops. Planck showed, no, light is actually a stream of photons, so it's a stream of particles. So this is the real world, okay? So I think we have to keep this in mind when asking what is the dark matter, because that's the complexity of stuff that we already know. Now, this business of particle wave duality, 100 years ago, people, big mystery, etc. Why is this particle? Actually, we understand this now perfectly well in the context of quantum field theory. And by the way, that's what we can contribute to the issues of dark matter, is that we know quantum field theory. I mean, I think we all took class, or should have taken a class, or will take a class. So what quantum field theory actually gives the ultimate description that we believe in. And what does it say? It says that everything is a field. The field has a set of modes, particular kinds of way of oscillating, waves, And each wave can be excited to a certain extent, but it has to be an integer extent. It has to be occupied by a certain number of quanta. So these are my waves. This is the time dependence, as you know. And each oscillator is quantized. So the Hamiltonian, so it's actually very simple as an idea, is the sum of energies in each wave times an occupation number, and then there are interactions in principle. There can be interactions. I think the business of physics is the business of removing layers of confusion. So often when we discuss quantum field theory, we expand the quantum field, so this is a scalar field, in terms of momentum eigenstates. But the reason we do that is because quantum field theory was invented to understand quantum electrodynamics and scattering processes like Compton scattering, where you go from momentum eigenstate to the momentum eigenstate. So now, however, if you want to use it for dark matter, you better change that attitude. You should expand the field. Maybe it will be more practical to expand the field in any set of modes that's of interest to you. And the only requirement, so instead of putting e to the I p dot x, I've just put any modes. And the only real requirement that you have is that the modes form a complete orthonormal set. And so they satisfy this completeness and orthogonality relations. Now, to tell you some more stuff that you know very well, well, you know some fields very well because they are the fields of the standard model. But no, none of the known fields are what you want for dark matter. Well, most of them actually are unstable, so that's not good. Some of the stable ones, like the baryonic quark fields, the electron, they interact too strongly to be the dark matter. So they're too visible. And then you can have neutral baryonic matter. The trouble with that is that it doesn't fit with nucleosynthesis, and it doesn't actually fit with the cosmic microwave background, because those studies tell you that the baryonic content is what 5% was the dark matter content, it's 26%. Okay. So this is another thing I don't need to tell you, but still like to remind you. You know, when you do physics, most of the time you're able to give a complete description. But if you're going to describe the dark matter fluid and its full physical content, in principle, what you do, you give a state of the fluid in Hilbert space by giving, considering that any number of modes can be occupied by any number of particles. Actually, I'm assuming bosons. Fermions, it can only be 0 or 1, but bosons can be 1, 2, actually up to 100 or whatever. And for each of these possibilities, you must give a probability amplitude. So, of course, this is extremely complicated, and people don't easily want to face up to such complexity. I'm just reminding you that that's actually the true reality, unless you're somehow denying some tenet of your graduate physics education. Okay. So single particle quantum mechanics, which we study, corresponds to the case when one mode is occupied and all the other ones are empty. So there's a particular mode for that field. It has a wave function. It satisfies the Schrödinger equation and the non-relativistic limit. And perhaps something that's overlooked, actually, the electromagnetic field is the same way. If you say you have one photon, it has, in fact, wave function, and it satisfies the wave equation. So essentially, these two equations are the same, even though we often think this is a question from the education on electrodynamics and this in quantum mechanics. But actually, they are both wave equations for modes of the field. Now, the full wisdom that we think applies to dark matter is that it's described by quantum field theory. But we like to think, actually, when we go around, it's too complicated. And we like to think about the classical limit. And there is also great richness to this, because quantum field theory actually has two classical limits. It has a classical particle limit where you go from QFT to quantum mechanics, and then from there you go to classical mechanics. This is the case where you take, in both cases, you take h bar goes to 0, but here you keep the energy of the particle and its momentum fixed. And since the energy is omega, h bar omega, omega must go to infinity. Likewise, the wave vector must go to infinity. What that means is that it's a wave packet that you can no longer resolve because its frequency of oscillation is so fast and its wavelength is so short. So it becomes a wave packet. And of course, if you're going to apply this to dark matter, you're going to have to say there's many, many such particles. There's also the classical field limit, which is a different limit where you take h bar goes to 0, keeping the energy and the momentum fixed, but for every mode, you let the number of quanta go to infinity. So now the frequency and the wavelengths are kept fixed, but the number of quanta go to infinity when h bar goes to 0. And that's how you obtain, say, classical electrodynamics from quantum electrodynamics. Now, just when do you believe one description or the other? What is the criterion? Well, here's a rule, of course, that we know. The dispersion in space and the times the dispersion in momentum must be bigger than h bar over 2. The particle description is valid, let's say, if the wave packets are much smaller than the interparticle distance. But because of the uncertainty principle, this puts a limit on the momentum dispersion, right? Since the wave spatial dispersion has to be small, the momentum dispersion has to be big enough. And when you look at this too, that means that the space density must be small, much smaller than 1 in units of h to the -3, where h is Planck's constant. So basically, your particle description when the phase space density is small. Oops, this is my friend, collaborator Jim Ipser, because he's actually the one who forced me to think about phase space. So I'm grateful to him. So here's phase space, X and P. So here are particles in phase space. And I'm repeating what I said before, but this is this picture. There's a spread in physical space, a minimum spread, therefore, in momentum space. You have a particle description, but the distinction is sufficiently, within these globs, is sufficiently large that you have separate little globs. And that's when the phase space density is much less than 1 in natural units. Now, the wave description is valid in the opposite case, where the phase space density is much bigger than 1. When that happens, all the little wave functions overlap, and you can't tell them apart, but you still have a density in phase space. And actually, that is the most general description. And you have a momentum at this position, we have a momentum dispersion for this fluid and the density. But mind you that this sheet can fold in phase space, and you can have several flows, each with their own density and velocity. So the wave description is valid when the quantum degeneracy is large. Okay, so the title of the talk was how, I'm going very slowly, and I know I know Luca is a very sweet guy, but Zurab is not going to let me go over 1 hour.
It's okay. Good.
Okay. No, I want.
Okay.
Is this necessary?
I think so. For the video.
Oh, okay, right, for the video. Okay, well, this is also stuff I think that you know very well, but let's say it anyway. There is 2 basic dark matter candidates. Actually, there's many, but they fall in these 2 categories, either particle or wave dark matter. So the WIMP is the archetypical particle dark matter. It has mass of 10 GeV. It's produced by freeze-out. This happens at a temperature of order 1/20th its mass, it turns out. But after they freeze out, their number is conserved, WIMPs and anti-WIMPs, but they are still coupled through weak interactions to the neutrino bath. And that stops at around 1 MeV temperature when they become actually kinetically decoupled. From this, you can calculate how many WIMPs today and what is their momentum dispersion. I'm just saying the dark matter density is 0.23. I don't know, it was 0.26 earlier, but it doesn't matter. You know, these numbers change a little bit, but the conclusions don't. We know the density, and I'm also going to talk about the homogeneous universe, because actually a lot of these issues are not so simple. And let's take the universe homogeneous, at least at the beginning, and then we can later take it inhomogeneous. The number density of WIMPs then is 1 per meter cubed roughly, and the momentum dispersion we can calculate from what I said before, the 1 MeV kinetic decoupling temperature. And this corresponds to velocity of the WIMPs of order 10 to the minus 12 in terms of the units of the speed of light. That is roughly 1 kilometer per year. Okay, so they move very slowly. And the corresponding minimum dispersion in physical space is 15 micrometer. And that determines a phase space density of 10 to the minus 13. And so, as you expected, the WIMP fluid is highly non-degenerate. Axions are the complete opposite. Their mass of order 10 to the minus 5 eV. I'm talking about cold axions, not thermally produced axions. They're produced, say, by vacuum realignment or by string decay or so. Then their momentum dispersion when they are produced is for the horizon at QCD time, which is roughly at the time of 10 to the minus 7 seconds, when the temperature is 1 GeV. If you then ask today, and I'm talking about the homogeneous universe again, the density is over order 10 to the 8 per centimeter cubed. And the momentum dispersion is obtained by taking the momentum dispersion 1 upon T1 at QCD time and then just stretching by the expansion of the universe. And that corresponds to velocity of 10 to the minus 17 times the speed of light, or 30 centimeters per year, which is the same speed as the speeds of the continents, you know. Continental drift is centimeters per year. So the axions move extremely slowly. But to think of one axion moving doesn't make sense, because the axions are cold. Each one has a wave packet that is spread. The spread of the wave packet is of order, the inverse of the momentum dispersion, is of order 10 to the 17 centimeters, which is actually a fraction of order 1 almost of a light year. And the degeneracy, the phase space degeneracy, the quantum degeneracy is 10 to the 61. So it's extremely degenerate, whereas WIMPs are extremely non-degenerate. So this suggests that maybe we can distinguish axions from WIMPs. Now, I know GP is there. He is going to find axions. He will find sun. And then he is going to distinguish, he's going to say the dark matter is axions. But I'm talking about, and so people want to do this with WIMPs too. And actually, the large popularity of axions is manifested by the here, has to do to the people not finding WIMPs, I think to a large extent, right? But actually my goal is to ask, is it possible, perhaps, since they're actually very different kinds of dark matter, to distinguish them on observational grounds? Okay, well, both of them should satisfy this. If WIMPs, if the dark matter is WIMPs and we're on the non-relativistic limit in the linear regime, they have a density and they have a velocity. The velocity is that of the Hubble flow, and peculiar velocities, deviations they form in the linear regime. And they satisfy the continuity equation, and they satisfy this equation, which just says that the WIMP exclusively responds to the gravitational field that's present. And the gravitational field is not just due to the WIMPs, because there's also other stuff like dark energy and baryons. Now, if you have axions, it's highly degenerate, and therefore you would think it behaves like a classical field. And so you may ask, well, does that behave, does it have the correct properties? And it turns out that yes, it does in the non-relativistic limit, and on distance scales much larger than the wavelength. This goes back to Newton and Huygens. You could not tell who is right unless you can resolve the wavelength. And that's true here too. So more formally, let's say this is a scalar field like axions. It satisfies a wave equation in a universe with space-time curvature. So this is general relativistic here. And this is the frequency. I'm actually trying to point out something here that is often not stated, but perhaps should be stated. In classical field theory, there is no such thing as a mass. If I may be so saying it so emphatically. Because the mass is the energy of a quantum, and the classical field theory doesn't have a quantum. So in the classical field theory, you should not talk about the mass, but you should talk about omega naught, which is the frequency of oscillation of the field when it has no momentum. Okay, in the non-relativistic limit, there's a simple transformation that's well known by which the scalar field is replaced by a wave function. Here it is written down here. And the non-relativistic limit means that the time dependence in this wave function is much less than the mass, basically. So actually, I know I just said one should not do that, but I'm going to do it myself. As I'm talking about I'm going to talk about the mass, but I just want to emphasize in the classical field theory, you have omega naught. But okay, let's introduce, for the sake of making the speech easier, speed of light and h bar z equal to 1, then the equation for this field, although we're talking about classical field theory for this wave function, is exactly the Schrödinger equation. And it has a density, and it has a velocity. The velocity is 1 upon m times the gradient of the phase of the wave function. I think you No, this is very well known in condensed matter physics, where it describes a super fluid or by a wave function. It has a density and then there is a phase. The gradient of this phase is the velocity. Maybe there's a good point to notice that if so, then the curl of the velocity is zero. The density and the velocity satisfy the continuity equation. And then do they satisfy the Euler equation? Because earlier I'd said, what you want is stuff that satisfies this equation. And actually it has an extra term. And this extra term is also gradient of Q. And Q is called quantum pressure. And I think it's a nice example of poor choice of words, which is plentiful in physics. Q is not a pressure. It doesn't have, in fact, the dimensions of pressure. And it has nothing to do with quantum mechanics, because I just said it is a property of classical field theory. But in some way, the word doesn't, in fact, stick. It does express the fact that in quantum mechanics, if you take a pile of stuff, it will spread because of the Heisenberg uncertainty principle. Whereas in the presence of any interactions, right, it will just spread. This is really what this term does for you. Take that into account. This is the expression of this quantum pressure in terms of the density and the mass. And this has an effect because the equation for the growth of density perturbations in the early universe, say for WIMPs, is this equation without the last term. But because of the quantum pressure, you have this extra term. And as was pointed out by a club of Malomet and Zeldovich, actually a long time ago already, this introduces a Jeans length. And this Jeans length, if you take, say, the density of the homogeneous universe and a mass of 10 to the minus 5 eV, is of order 10 to the 14 centimeters. And so actually, it is very short. It is very short compared to astrophysical scales, which are for the kiloparsec, 10 to the 21 centimeters. It is much less than that. But that's because I took the axion mass to be 10 to the minus 5 eV. Now, it has been proposed that the axion could be much lighter, maybe 10 to the minus 21 eV, 10 to the minus 24 eV. And then the Jeans length becomes of order kiloparsec. This is 3 kiloparsec, 10 to the 22 centimeters, which is of order the central region of the galaxy, right? We are of order 10 kiloparsec from its center. And I like to point out, as far as I know, the first one to point this out propose this was Sanjin Sin, because he was a postdoc in Florida when he did this. But this has been picked up by many other people, very famous people, and it has been simulated on computers by, someone should pronounce this name because it's actually a Chinese name. I'm told I should say Sure. Is that right? And then, and many others. And there's a very nice review of this proposal by Lamouy, Ostreicher, Tremaine, and Witten. And we'll talk about this tomorrow, according to the title given for the seminar tomorrow. Wave dark matter, I think. So, in fact, a classical field theory like you would expect for axions, because they're very highly degenerate, does in fact fit the bill if you go by this criterion. It satisfies a different equation, but the role of quantum pressure is only felt on very small scales, unless you take the mass very small. And so a classical field is also acceptable dark matter. But we know, and this is why this lengthy introduction, we know, because we went to graduate school, that the actual world is quantum field theory. So if you're talking about just particles or classical field, you are making an assumption. And the assumption may be valid, it may not be valid. You have to check. And I'm going to check in the case of classical field theory. And classical field theory, if you describe the quantum field, and we agree, isn't it, that the axion, if it is a dark matter, is going to be a quantum field, not a classical field. So if you say it behaves like a classical field, what you're saying is that there is one mode of the quantum field with a particular wave function, psi, that is very highly occupied. Say all the quanta are in this one mode. And so this is here the wave function of the state of the dark matter. But for this to be actually a correct description, we should ask, do the quanta actually stay in this particular mode, in this particular state? So I say, yes, they will for a while, but actually they will leave. And you should certainly expect them to leave on a time scale longer than the thermal relaxation time. And I think that that is quasi-self-evident, because thermal relaxation means that the fluids interacts, self-interacts, say, and it goes to states that are more and more likely, so entropy goes up. And entropy, as you know from course on statistical mechanics, is counted differently in classical mechanics than in quantum mechanics. So for quantum system, if it thermalizes, it will go to a different state than the classical version of the system. And I'm very happy to give this next part of the talk because Elisa is sitting here and we did this work together. Is there a question? Yes, please. I go back a couple slides.
Why of this that that is the quantum state corresponding to the classical field? Let me briefly discuss why is that quantum state and not a theoretical state?
Yes, you have a very good point. I hope to go over this, but you're right. We can just ask the same question about any oscillator. I say this oscillator is highly occupied, and I describe it by the state, which is an eigenstate of energy, an eigenstate of the occupation number. But as you point out correctly, it need not be like that, and probably is not like that. It could be the oscillator could be in a coherent state, or actually it could be in any state that is highly occupied. But that actually is not going to make any substantial difference. In principle, it does make a difference, but that difference is going to be extremely difficult to see in any way. You know, if it's a little bit like I take some oscillator and I give it a kick and I give it some energy, and you say it's in a coherent state. Well, right, because you are looking at it, but as far as dark matter is concerned, you're not going to be able, at least as far as I can see, going to be able to look at it in such detail. You're just going to be able to say there's a certain amount of energy there. Is that okay? I can't see you.
But if I think of classic,
Yes. No, that's only true if it does not interact. It's for, sorry, if there's no interaction, that's true. But if it is interaction, this is part of the question that Elisa and I were interested in this by doing this work.
So we are not detecting. Because comparing the classical equation, we don't have
Yes. Thank you for pointing that out. Yes, exactly. We're going to consider interactions. And you may say, well, it's a collisionless fluid, there's no interactions, but it does have gravitational interactions. Yes. Okay. So Elisa and I, we looked at 5 quantum oscillators, and they were, as you are emphasizing, interacting. So we had interactions between them, and they're described by this. And oops, okay, no, it's okay. And for some of technical reasons, we take the frequencies of the oscillators to be omega-1, omega-2 is twice omega-1, omega-3 is 3 times omega-1, and so forth, and omega-5. And we actually have interactions between them when K plus L equals I plus J. This is because the axions actually interact in the condensed regime, and that is the relevant type of interaction in that case. This takes some little time to explain, but I don't have the time. Okay, so we looked at simulations where you have 50 quanta amongst, I'm sorry, I should say 5 oscillators, typo. The number of system states is then over 300,000. So the Hilbert space has that many states, and the wave function is some number, complex number for each state, an amplitude for each state. And we start with some, the eigenstates of number eigenstates. We actually also did coherent eigenstates, but doesn't change the answer. But as you point out, we do have interactions, and that's very important. So we do have interactions. We start, for example, with 25, 15, 5, 5 amongst the 5 oscillators, and we let them rip. We calculate for this number of particles and total energy, what are the thermal averages, the most likely values, or actually I should say the expected values, excuse me, amongst the 5 oscillators. Oh, so we integrate the Schrödinger equation, calculate these in the quantum theory, and then we had estimated the relaxation time to be of order 0.6 in the units of the simulations, time units of simulation. And 0.6 is over here. And these are the initial values. These are the calculated thermal averages. And you see that, in fact, consistent with expectations, in the quantum theory, the full exact quantum theory, the expected values go to their thermal averages on the expected time scale. Okay. And oops. Oh, what happened? Go forward or back? Oh, okay. Sorry.
It takes a minute.
No, I let me not go over time. Oops. Okay. So what I'm saying, I don't know why this slide is here, but oh, oops. Okay. We also simulated the classical evolution, which that's very simple. And you see that the classical evolution is similar to the quantum evolution at the very beginning, but after, if you look at it a little later, it's completely different. So the classical evolution tracks more or less the quantum evolution in the sense that this line, for example, goes down. This line also goes down in a similar way, and so forth. On a time scale, roughly of order the relaxation time scale, but then it differs from it, as I think one should have expected. So the quantum system thermalizes on the expected time scale. That's what we learned. The classical system, as it turns out, does not thermalize even after a very long time. Something got messed up here. This is actually something that was actually already pointed out by Fermi, Pasta, and Ulam. When the first numerical computers arrived, they put this problem, the classical problem, on the computer, and they found this phenomenon that it never thermalizes. And actually, I think Elisa and I agreed that the reason this happens, that it doesn't thermalize in the classical system, is that it is not sufficiently rich. It has too few degrees of freedom. It only has 5 degrees of freedom, which the energy flows from one to the other in some random way. And this is not true about the quantum system, which has 300,000 degrees of freedom. And the classical system tracks the quantum system only briefly. Okay. So the question then is, does it thermalize? Because if the axion field thermalizes, you should not expect all the quanta to stay in that single state. You should expect the quanta to go to a state of highest entropy. So does it thermalize or does it not thermalize? So we're neglecting the axion self-interactions because they are too feeble. Actually, they are important when the axions first appear at the QCD time, just considering gravity. So here you are looking at this glob of dark matter, and you're sitting over there, and you're asking, what is it? Is it axions or is it WIMPs? And I took this glob to be an ellipse because it's easy on PowerPoint. And I took it to have sharp lines because it's easy on PowerPoint, but that's a detail, don't worry. It's important that it's of order like here. It can have any shape and doesn't need to have sharp edges. Well, let's say, suppose there's WIMPs made of WIMPs. In this glob, there are 3 times 10 to the 47 WIMPs. And each one can be in 10 to the 13 states before it meets another WIMP. So it's that highly degenerate. So in other words, you can reproduce this blob with extreme accuracy if the dark matter is WIMPs. But let's suppose the dark matter is axions. Then in this glob, there are 3 times 10 to the 62 axions. Okay. But there's only 10 to the, there's only 30 states in which you can place the axions, because the axions are highly degenerate. There's 10 to the 61 axions in every state. In other words, because they are spread, you cannot make any glob that you want. You're very highly restricted. Basically, wherever you have some density, you have a correlation length. Because if the momentum dispersion is delta P, then the axion field has to be quasi-homogeneous on a length scale, which is the inverse of this momentum dispersion. So my time's up, so I'm gonna just summarize. Okay, but I'm gonna go very fast, okay? So I can talk individually if people are interested later. Okay, this says the same thing. Now, if the field is homogeneous on a length scale L, then it means it has gravitational fields on that scale, which are the density times the length times G. So in a homogeneous universe, the gravitational field is supposed to be 0 on a particle. And that's true on average in both the WIMP and the axion case. But in the axion case, you should expect that although the average field is 0, the field fluctuates with this value of the field delta G. Now that means it accelerates particles. And you can ask how much time does it take to reorganize the momentum distribution entirely when that happens. And today, if it didn't happen before, it happens in 24 seconds, just like that proof. Actually meaning it did happen before. When it does happen, it makes a Bose-Einstein condensate because all the conditions for Bose-Einstein condensation are satisfied. With Charlie Yang, who was the first person on the list that I showed of collaborators, we calculated when this happens first in the early universe. And I have to go fast. This happens when the photon temperature, so for the 400 eV, we claim that in a homogeneous universe, it goes from this to that. So that's a difference now between axions and WIMPs. WIMPs don't do that. Now, does this have observational consequences? In the case of WIMPs and also of a classical field, you can show, because the right-hand side of Euler's equation is a gradient, that you will never produce a rotational velocity field. Rotational velocity fields, you have no vorticity. Whereas in the case of axions, on the time scale of thermalization, they can produce vorticity. When a Bose-Einstein condensate is torqued up, it will have vorticity. Then you may ask, well, is that observable? So here I have a cartoon of a galaxy. Sorry for my very crude pictures on PowerPoint. Galaxies are torqued up by total torquing. In the case of CDM, the velocity field must remain irrotational. In the case of axions, it can acquire vorticity. The caustics are different in the two cases. This is the case of WIMPs, and this is the case of axions. So that brings me to my conclusions. Oops. The velocity fields of WIMPs and classical field dark matter is necessarily irrotational. Axion dark matter forms a Bose-Einstein condensate. Its velocity field becomes irrotational, becomes rotational when the torque is applied. The inner caustics are different in the two cases. So the answer to my question in the title is, provided you can observe the inner caustics of galactic halos, you can tell apart axions from WIMPs.
Thank you very much. Yeah.
comment on gravitational coupling to baryon?
The gravitational coupling of axions or WIMPs to baryonic.
Gas.
Okay, so but let me ask GP in what context? If you go to say the cosmic microwave background, that is included, right? That is to say, this fluid, cold collisionless fluid has a density, therefore there's a gravitational field that's included, and plays an important role. But that's presumably not what you asked. I think you mean in another context. Yeah, so the organizers were so kind as to let me give a talk during the conference last week. And this material is largely preparation for this, because actually, in reality, I claim there is observational evidence for caustics, and they are of the kind expected from axions, not from WIMPs. So actually, I claim that there's observational evidence for axion dark matter, for this somewhat long-winded argument. So how can you see that caustic is because of the gravitational interaction of the caustic with the baryons. So the evidence would be a caustic ring in the Milky Way disk gravitationally attracting the baryons around it. And I claim there's evidence for that. But I thought today I just tried to go slowly and say that this is in principle possible. Or if you don't think so, which of course, skepticism is the rule in science. I'm not saying you have to believe anything, but I would like to know where is the weak point in your mind in this claim that in principle you can distinguish axions from WIMPs by looking at the question whether dark matter is vorticity, which is related to the question of what inner caustics it makes in galactic halos. Yes, please. Yes, correct.
So, for example,
yes.
if I are going to higher loops, we can start triggering interaction with different modeling. We can now, so this, for example, in a body. I don't understand how from this you can extrapolate to gravity, because ultimately the way in which takes place depends by the microscopic dynamics and the interaction we have. And so I don't understand how you can estimate from just the value of the coupling that we have. The value of coupling you can here that there must be compensation rate for the classical because of gravity.
So first, it has nothing to do with the loops.
Well, compensation does. If I do loops and it's not integrated loops, I can.
Yeah, I think, yeah. So this is one of the reasons I like to go slowly, because it's often stated in quantum field theory that the classical limit is obtained by only having 3 graphs. Only have 3 graphs. I think the reason you say is you go to loops, because I'm saying it's a property of the quantum theory. And the common statement is that classical theory is 3 graphs, quantum theory is loops.
But I mean, your order expansion is
The expansion, I'm sorry, the well, I don't think I gave an how do you say, systematic expansion in the occupation number.
Yeah, I mean, another view. I mean, when you do material with work happening from you see thermalization when it's starting to reduce, for example, so that comes from a microscopic dynamics, and from value of cutting, I can tell here what would be the time scale of breaking of my unity description. But that doesn't mean that they're factoring the time scale at which the explain. It's definitely like a microscopic time.
Yeah, I think this phenomenon has nothing to do with loops.
I mean, you're okay. Anyway, you're describing a breaking of the meat. What it is that you mean by that? I mean, when you talk about gravity.
So by thermalization, I mean that the system of particles takes its states or moves towards its state of highest entropy for given energy. So when you have Bose-Einstein condensation, say, in rubidium atoms, which is now very well observed, it has nothing to do with loops. It just has to do with quantum statistics. Okay. So it's actually a misunderstanding that's very common taught in quantum field theory courses, that the classical limit of quantum field theory is obtained by ignoring loops. Well, that's true if you don't have degeneracies. Obviously, there are distinctions between quantum field theory and classical field theory when you have a degenerate fluid. And the distinction has to do with the fact that the way you count entropy in the two cases is different. It has nothing to do with loops. So I think once more, I feel that making progress in physics has to do with removing layers of confusion. Yeah. No. Yeah. No, I did go very fast here. So I think the crucial point is when you estimate what is the rate at which all the full momentum distribution of the axions get modified by gravitational interactions. I take that to be the thermalization timescale. To estimate it, I take the typical fluctuation in the gravitational field when I take into account that there's not just a density, but fluctuations in the density having to do with this momentum dispersion. The gravitational field fluctuates so that you have a typical gravitational field fluctuating, and ask how quickly, and I did go very fast, I just ask how quickly does it rearrange this momentum distribution entirely. And I estimate it to be 24 seconds today, if it didn't happen before. Then I simply say, and of course I was not there to observe the phenomenon, but I think it's very logical, that when you rearrange the momentum distribution entirely, it will go to a state of highest entropy. That we know, as Einstein pointed out upon reading paper by Bose, that actually for a highly degenerate gas, whose number of particles is conserved, after it has thermalized, it must make a Bose-Einstein condensate. And I did go very fast, but if you ask what is the state of highest entropy, it is one in which you put all the particles in the lowest state, the state of lowest energy possible, and you produce a thermal distribution above that, in principle. But the phenomenon of Bose-Einstein condensation is very, sorry.
So this is not necessarily just quantum phenomenon is possible. For example, if I take number and I start looking around the different
So let me see whether, okay. No, okay, that's actually an interesting point. So let's take a classical field theory, take lambda 5/4 interactions, right? Let's do that. Let's have it, give it some momentum distribution like this.
If I do that, I know that I can.
Wait, no, you have a condensation in the zero mode at first, but then the condensate will evaporate.
No, I keep track also of the map of the number. But I see that I converse over.
No. In the case of a classical field, if you thermalize it, the end result of thermalization is a so-called ultraviolet catastrophe, where you put equal energy in every mode available. But you're making a good, correct observation. Actually, if you do it on a computer, you'll find that initially, it does in fact condense also in the classical theory. But if you then wait longer, what happens is that every mode, actually all these particles, they will get hotter and hotter and hotter, and your condensate will disappear, and you'll have this so-called ultraviolet catastrophe that Rayleigh actually first pointed out when Boltzmann gave the rules of statistical mechanics. He applied them to Maxwell's theory, and he, as we all learned this in statistical mechanics, that you have an ultraviolet catastrophe. That's completely inconsistent with observation, right? Because actually the specific heat per unit volume is infinite. Right, so they are important. So this is one, thank you. Please go ahead, yes.
These are like scaling behavior. So what if I take on quantification now, I start having scaling. Some of that is for the direct and other but the point is that this happens when I start allowing for the cross interaction of cosmos with loop level. And the fact, okay, by loop level here I mean that if the occupation is large, then it becomes a sort of tree level. The occupation is large, it's still not the H bar.
No. I think we disagree on the question whether it involves loops. I think when Einstein pointed out Bose-Einstein condensation, he didn't know about loops. Loops are completely irrelevant. And so I think it points to, I think, a very widespread misunderstanding that you need to have loops in quantum field theory to have deviation from classical behavior. I don't think that's correct. Definitely, classical field theory, when you thermalize it, it produces ultraviolet catastrophe. And you don't have that in the quantum theory. It's actually one of the fundamental lessons that we learned at the end of the 19th century. So it has nothing to do with loops. But later when you go to, and this is why I think it's true, that making progress is removing confusion. Because when I was taught, when I took a course in quantum field theory, simple, the loop expansion is an expansion in powers of H bar. That is correct. Therefore, then, let me finish. Okay. Therefore, in the classical limit, when you take H bar goes to 0, you just have 3 diagrams. That is everything that you know about the classical. That I say is incorrect.
Yeah, because your occupation number is one of the H bar. So when you take the limit H bar to 0, those are the interactions that you need to obtain. So how do you recover? You do lose level and then because the occupation number is still going to break, basically that becomes like the level.
But you have interactions even at tree level.
Yeah, but I'm saying to account for that, you solve very microscopically. How is it going on? I'm saying that because of that, there is a certain value, but
We calculate the relaxation time due to the tree level process, which is I'm sorry. So this is if you like to use the language of quantum field theory, this is the relevant diagram. And the reason it happens very fast is the momentum transfer is very small. When you go from highly occupied states to highly occupied states, you have this Bose enhancement factor. Because the fluid is very cold for those transitions that you have this Bose enhancement, the momentum transfer is very small, and therefore this interaction rate becomes very large. But it doesn't involve loops. In fact, it involves loops. I don't know how to introduce loops in gravity. So, okay. So I did not use this language, but I just used the language of just fluctuations of the gravitational fields, but that actually is completely equivalent to this. So if you take this diagram and keep in mind that it is enhanced by the final state's occupation numbers, that only happens when Q is very small, you get exactly the same answer.
The questions? Not, we start from the other line, of course. Let's start again.
I like applause, very loud in this room.